Welcome my friends, welcome to my next lecture. Now in my last lecture I talked about the notions of differentiability and what is Cauchy-Riemann equations, and then what is the necessary conditions for differentiability, and then you know that if my function is complex differentiable, then the corresponding real part of f and imaginary part of f, which is nothing but u and v, they are satisfying Cauchy-Riemann equations. Then I have discussed that not satisfying Cauchy-Riemann equations implies that my function is not complex differentiable. However, if my u and v satisfies Cauchy-Riemann equations, still I can say that my function is complex differentiable. Answer is no. I discuss explicit examples. So now today's lecture I will talk about sufficient conditions for differentiability. That means I will show you, or I will tell you that if my functions f from c to t, which is of the form u plus iv, then only satisfying Cauchy-Riemann equations will not imply the existence of complex differentiability. I need something more. And what is that something more? And if time permits, I'll start the notions of what is called analytic functions, and then harmonic functions, and how to calculate harmonic conjugate, and then later what is called multivalued functions and its branch. Okay, so as I said, so necessary conditions for differentiability I have discussed. Now let me talk about what is called sufficient conditions for differentiability. Now as I said, it is automatic. Now you can guess, at least if you know the necessary and sufficient conditions for existence of total derivative for a function from R2 to R2, now you can guess what sort of sufficient conditions you will have for the existence of complex differentiability. Because if my functions f from c to c, and if I write it at the form u plus iv, then you can think about it's a map from R2 to R2, and then f is of the form u comma v. Now existence of the total derivative of f implies of course the existence of partial derivative of u and v and their continuity. The only part was remaining to talk about what is called, so that was talking about what is called total derivative, or from functions from R2 to R2. Now I have a functions from c to c, and that functions I can think about from R2 to R2. So therefore for R2 to R2, if I talk about the differentiability, so only existence of partial derivatives and their continuity implies the existence of total derivative. But what about complex differentiability? Complex differentiability, it's needed something more. What is the necessary condition for complex differentiability? That means satisfying Cauchy-Riemann equations. So therefore now I have, if I state my theorem like that, okay, look, sufficient condition. Suppose f of the form u plus iv, and I want to talk about the existence of complex differentiability at the point z0, which is x0 plus y0. Then look, first one is that first order partial derivative ux, ui, vx, vy exist in a neighborhood. That is very important, because I want the continuity of the partial derivative. That means only existence at a single point, I cannot talk about the continuity. So I need the existence in a neighborhood. And then second one is that these are all continuous at the point. So that from, if I think about from R2 to R2, so existence of partial derivatives and their continuity implies the existence of total derivative if I think about from R2 to R2. But what about complex differentiability? That is the extra conditions, that yes, the earlier two kind of conditions should be true. That means the partial derivative should exist in a neighborhood of that point, z0 is equal to x0 comma y0. Not only that, the partial derivative should be continuous, and number 3 is that they satisfying Cauchy-Riemann equations at that point z0. If these three conditions true, then I will say that my function is complex differentiable, and not only that derivative is of the form ux plus ivx or vy minus iuy. So therefore, if we just kind of compare the differentiability from R2 to R2 and differentiability from C to C, there is a gap. There is a gap means there is a serious so it's for example, just let me talk about in this way also. So suppose you have a functions from C to C, f is equal to u plus iv, right? So what is the derivative? Suppose my function is complex differentiable. So derivative at the point z0, you can say that this is ux at the point x0 comma y0 plus I times vx at the point x0 comma y0, right? Now think about the functions from R2 to R2, and if I want to talk about the differentiability at the point say z0, which is x0 comma y0, what is the total derivative? Now total derivative at the point say x0 comma y0, if you remember, it's a linear transformation, right, from R2 to R2, right? Now that linear transformation you can write it explicitly, because any linear transformation from R2 to R2 is a 2 cross 2 matrix. Now what is the 2 cross 2 matrix? Jacobian matrix, you know, na? So what is that? What is, since f is the form u and comma b, so therefore this is ux at the point x0 comma y0, then ux, then ui at the point x0 comma y0, this is vx at the point, or maybe it's up to you. Ux at the point x naught comma y naught, ux, I think this is correct, uy at the point x naught comma y naught, then vx comma y naught or vy, right? True cross 2 matrix. So if f is of the form u comma v, then you can write your linear transformation f prime at the point x naught comma y naught, that means existence of total derivative from R2 to R2, which is of this kind, ux uy vx vy, right? Now if I have a function, same function, if I think out from C to C, which is u plus ib, and what is the derivative? Ux plus I times vx. So what will go wrong? So one time if I think about from C to C, it will, like, it involves only the partial derivative with respect to x variable and partial derivative of v with respect to x variable, that's it, or ui vy. However, to talk about the total differentiability of the same function, if I think about from R2 to R2, it involves 4 things, right? It's a 2 cross 2 matrix, right? So ux ui vx vy. So how they are like from 2 cross 2 to like only 2 variable dependence? Here we will have independence, right? ux ui vx vy, like, so like you can think about these 4 objects are somehow independent. So if I have a different ux, different ui, different vx, different vy, then the corresponding derivative will be different. But this is actually in terms of, instead of 4 you will have 2, and that gives you what is called CR equations, because Cauchy-Riemann equations implies that they are actually, even though if I think about from R2 to R2 differentiability, even if it is a matrix 2 cross 2 matrix where 4 independent objects are there, but whenever I am talking about the complex differentiability, it's actually boils down to from 4 object to 2 object. And why that dependency is there? Because of Cauchy-Riemann equations. Because Cauchy-Riemann equations will give you a relations ux is equal to vy and ui is equal to minus vx. So therefore this and this has related. So therefore even though in total differentiability for R2 to R2 I am dealing with 2 cross 2 matrices, but if whenever I reach to the complex to complex case, because of Cauchy-Riemann equations, and so there is a relations between ux and ui and vx and ux vy and ui vx. So and that gives you this kind of, out of 4 independency, 2 gives you the 2 independency because of Cauchy-Riemann equations, and that is exactly the major difference for differentiable functions from R2 to R2 and differentiable functions from C to C. For R2 to R2 differentiable functions, if I have a component functions u and v, only the existence of partial derivatives will tell you the existence, of course, existence as well as continuity will implies the existence of total derivative. However, if I think about that functions f is equal to u plus iv as a complex derived functions of complex variable, so only the existence of partial derivatives and their continuity will not imply the existence of complex differentiability. I need some extra one. What is that? That is the Cauchy-Riemann equation. That means, so not only ux ui vx vy exists, they should satisfy our equations. So that is why from 4 independency or 2 cross 2 matrix, it boils down to what is called 2. From 4 to 2, and that is because of Cauchy-Riemann equations. So that's the major difference. So therefore, if I relate from differentiability of R2 to R2 and differentiability from C to C, it automatically gives you this should be the appropriate sufficient conditions for the existence of the complex differentiability of my functions at the point. Okay, so let me just say once again. So if I have a functions f from u plus iv, and if I want to talk about the existence of complex differentiability of my functions f at the point z0, which is x0 plus I y0, so what I need that if I write my functions f is equal to u plus ib, then I need the existence of partial derivative of u with respect to x and y variable. Similarly, existence of partial derivative of v with respect to x and y variable in a neighborhood of the point x0 comma y0. All the partial derivatives should be continuous. And third one is that this partial u and v should satisfy what is called Cauchy-Riemann equations at the point x0 comma y0. If these 3 conditions satisfies u and v, then I will say that the functions f is equal to u plus ib, which is complex differentiable at the point z0. Okay. Anyhow, so I am not going to prove that theorem, okay. So maybe later on if time permits I will discuss the proof, but for the time being, so you just assume that yes, this is the theorem. So proof part maybe later on I will talk about. So let me just see some examples, okay. So this is very standard examples, okay. For example, if I take f is a functions, complex valued functions of complex variable, suppose whose real part is e to the minus x cosine y, and so v part is e to the minus x sine y. So therefore what is your u? U of xy, you can say that this is e to the power minus x cosine y, and what is vy? V of xy, So this is u plus iv, you can write it. So this is should be e to the minus x sin y, right? So now what is u and what is v? This is exponential function and sine function and combinations, so very nice functions. Okay, so all the partial derivatives of u and v with respect to x and y variable exist. So now to talk about the differentiability, complex differentiability, just if I want to use the earlier theorem, so I need to just check at which point they are satisfying Cauchy-Riemann equations. So you have the explicit expression of ux, uy, vx, vy, perfectly alright, because these functions are nice. Okay, now for any z satisfies Cauchy-Riemann equations. Okay, so I have explicit expression. Now by looking at the expression, look, ux is equal to vy, right? Ex is equal to, sorry, vy, it is minus e to the minus x, yeah. So ux is equal to vy at each point x comma y. Similarly, uy is equal to minus vx at each point x comma y. So therefore, if I apply my earlier sufficient conditions, so my functions f of the form u plus iv, where all the first order partial derivative exist, they are continuous, because what is ux? Again, it is a combination of cosine functions and exponential function. It is a continuous function, and it satisfies Cauchy-Riemann equation. So therefore, by sufficient conditions for differentiability, since it is satisfying Cauchy-Riemann equation at each point, so therefore my function is complex differentiable at each point. So, okay, so therefore by the previous theorem, sufficient conditions for differentiability, fz is differentiable at each point. And what is the derivative? You have the expression ux plus I vx, you know what is ux, you know what is bx, so this is the corresponding derivative. Okay, this is very simple examples, just to show you that a function is differentiable using sufficient conditions for differentiability. Complex differentiable I am talking about, yes. Okay, so now this is another useful formula. Okay, what is that? Since z, the complex number, will have a representations in terms of r and theta, then is polar representation. So therefore, can I replace the Cauchy-Riemann equations ux is equal to vy or uy is equal to minus bx, that is the Cartesian one, to the polar form? Is there any corresponding polar form? Answer is yes, because I can write x in terms of r and theta, y in terms of r and theta, and therefore you just replace the corresponding partial derivative in terms of r and theta using the chain rule. That's it. So that's I have written. So this is Cauchy-Riemann equation, because sometimes what will happen to talk about the differentiability of a complex valued functions, it might happen that you just like transform that equations to a polar form, and maybe Cartesian form, if I write it, which will be more difficult to analyze, like to write that functions of the u plus iv form, where u is a function of x and y and v is a function of x and y. Rather, I can change it to xy to r and theta, and there you can have a nice expression of u and v, or very easy expression where you can talk about their like that functions u and v in terms of r and theta. So therefore, if I have some kind of Cauchy-Riemann equations in r theta form, and if I check that equations, then I can easily conclude about the existence of complex differentiability there. So that is sometimes useful to solve some problems. So this is I have written Cauchy-Riemann equations in polar form. Suppose f of z, which is z is equal to r e to the I theta. So this kind of polar representation you know. So therefore I am writing my functions f of u plus iv. This time u is a function of r and theta, and v is a function from r and theta. Then the polar form of Cauchy-Riemann equation turns out to be ur is equal, or v theta should be r times ur, and minus of u theta is equal to r times vr. Okay, and this is very easy to conclude, because you know x in terms of r and theta and y in terms of r and theta. In my earlier lectures you already know. So if z is equal to x plus iy and z is equal to r e to the I theta, then your x is nothing but r cosine theta, y is equal to r sine theta. Then you can calculate your partial derivative of u with respect to r variable and theta variable, that means ur and u theta, that means del u del r and del u del theta. Now since x is equal to r cosine theta, then use the chain rule. What is that? This is actually del u, so you can write del u del r, so that means del u del x times del x del r plus del u del y times del y del r, that you know, this is chain rule. Okay, and then you can calculate del u del x explicitly, because del u del x keep as it is. So del x del r you can calculate, because x is a functions of r and theta, so which will give you ex cosine theta plus uy sine theta. Similarly, del y del r you can easily calculate. Similarly, u theta you can calculate, which is minus ux times r sine theta plus uy times r cosine theta. Similarly, you can calculate vr, and similarly you can calculate v theta. So, but I want Cauchy-Riemann equations in terms of r and theta. So I know Cauchy-Riemann equation in the Cartesian variable, that means ux is equal to vy and uy is equal to minus vx. So now you have ur u theta vr v theta, and it involves ur u theta vr v theta involves ux uy vx vy. But since there is a relations of ux, uy, vx, vy, so therefore if I use the relations, it turns out that you can have vr is equal to minus uy times cosine theta plus ux sin theta, and similarly v theta is equal to uy r sin theta plus ux r cosine theta. Then by just looking at this expression u r u theta and v r v theta, you can conclude that r times u r is equal to v theta and minus r times vr is equal to u theta. So that equations you just keep remembering. That is the corresponding Cauchy-Riemann equations in the polar form. Because as I said, because this you might need to solve some problems, because you might write, or because you may find difficulties to write f of the form u plus iv in terms of Cartesian variable x comma y. Rather, you can write your functions in terms of u plus iv, where u and v as a functions of r and theta. So therefore, if I know the Cauchy-Riemann equations in that setting, then it will be very, you can easily conclude about the what is called complex differentiability at that point. So that is why sometimes this Cauchy-Riemann equations in polar form will be useful. Okay, so another Cauchy-Riemann equations you can think about as a complex form. What is that? This is very nice. It says that the Cauchy-Riemann equations, again, it's like a change of variable, you can think, like earlier one also change of variable. From the variable x comma y, now you have a variable r comma theta. Now same thing, you will have the change of variable, and then what is that form? It says that the Cauchy-Riemann equations in complex form, it says that del f del z bar should be 0. That means f should not contain any variable, what we call any term of z bar explicitly. That is very important. So that is why del f del z bar is 0. So because sometimes by looking at the functions, if you say that functions like f of z, so like for example if I talk about f of z is equal to z bar, right? So it involves only z bar function. So what is del f del z bar? So it is 1. So therefore this is not 0. So therefore it is not satisfying Cauchy-Riemann equation. So therefore my function is not complex differentiable. And that f of z is equal to z bar, it is not differentiable, and at each point of the complex plane, many ways you can prove, either through principal definitions or through Cauchy-Riemann equations or using this formula. So therefore this kind of expression of Cauchy-Riemann equations sometimes useful. So if I have a functions and you can just see that functions involve z bar explicitly, then you can easily conclude that del f del z bar it's non-zero, and therefore my function is not complex differentiable. Like for example f of z is equal to z bar. Okay, so what is that? Again same thing, you have a z is equal to x plus iy, right? What is z bar? X minus iy. So I can write x as z plus z bar by 2, and what is my y? Y is equal to z minus z bar by 2y. So again, by do the change of variable, you replace x and y variable by z and z bar variable, and again you use the Cauchy-Riemann equation in the Cartesian form, and then give some kind of relations with respect to z bar variable, like here I have done. So you have a x is equal to r cosine theta, y is equal to r sin theta. So I can write I can change a variable. I am changing xy variable to r theta variable, and using the Cauchy-Riemann equation in the Cartesian coordinate. So I am having the expression in terms of r and theta. Here also same. So what I am doing? So del f del z bar, which is nothing but del z bar of u plus iv, because f is of the form u plus iv. So therefore this is del u del z bar plus I times del v del z bar. Now as I said, so you have a z, I can write x in terms of z and z bar, y in terms of z and z bar. So therefore by chain rule, this is nothing but del u del x del z bar plus del u del y del z bar. Now keep as it is del u del x, but del x del z bar you can easily calculate using this formula. So this is okay, so this is for one and this is for this one. So if I similarly, so del u del z bar is nothing but this object, and I times del b del z bar, it is same by chain rule, del b del x del z bar plus del b del y del z bar. But you can easily calculate del x del z bar del y del z bar, okay, explicitly, because you have that expression. Similarly del x del z del y del z. So what it will give? So it should be del u del x. What is del x del z bar? This is nothing but half. What is del y del z bar? This is I by 2. Similarly this is half. This is I by 2. Do some algebra. So you will have half of ux minus vy plus I times ui plus vx, right? But in the Cartesian coordinate, you know, if my function is complex differentiable, that means ux is equal to vy and ui is equal to minus vx. So therefore this object is 0. So therefore del f del z bar is 0. So therefore you can say that CR equation in complex form is nothing but f should be free explicitly from the z bar variable. I have written. So note, a differentiable functions fz cannot contain any terms involve z bar explicitly. That is very important. It might happen that it should contain some z bar term implicitly. That might happen. But this equation tells you that it should not contain any term z bar explicitly. It might contain implicitly, right? One example maybe later on I'll talk about that. Even if it contains implicitly, then I can have the complex differentiability, but it should not contain any term z bar what is called explicitly. That is why you should focus on this subject explicitly. So now I think like notions of differentiability, necessary and sufficient condition for differentiability, couple of examples I have discussed. Now I come to the what is called a new concept, what is called analytic functions. So this is a new concept for complex analysis. So if I have a complex valued functions of complex variable, so this is the new notions of analytic functions in the complex analysis. So what is that? This is the in fact the one of the major notions of complex analysis, because it will have later on many impact, because that is the major kind of object. Like if I have a complex valued function of complex variable, you can have the analytic functions, and this is very important. So like for example, if I have functions from R to R, then you can have continuity, differentiability at a point, and so on and so forth. In complex valued functions of complex variable, analytic function is the one, the concept of analytic function, which is the major distinctions between the real valued functions. Okay, what is that? Let me just talk about the definitions, and more properties in my next lecture I'll talk about what is that. So analytic functions, or in some books they are saying that this is called holomorphic functions. So what is the definition? Definition is that let fz, suppose f is a functions, okay, defined on an open set S. Okay, suppose you have a functions f defined from some domain S subset of C which is open, taking values in C. Then I am saying that my function is said to be analytic in an open set. Okay, so you have a functions f from some subset A subset of C to C, and I am saying that f is analytic in an open set. What I demand, my function should be differentiable at each point. So I have a functions A subset of C to C, and suppose this is my complex plane, this is my set S. So I want that I'm giving the definitions that my function is analytic on an open set S if my function is differentiable at each point in that open set. Okay, one example, let me see using the definitions what functions I can talk about analyticity. Yes, if I talk about f of z, g of z is equal to, say fz is equal to z, g of z is equal to z square, these are very nice functions because this function is differentiable on the whole complex plane. So if I take any open set, it is differentiable at each point, so therefore my function is analytic. However, if I consider this function f of z is equal to z bar n, anyhow f of z is equal to z bar, it is nowhere differentiable, so this is not analytic. Now look, this function, this is very nice. So g of z is equal to mod z square. Now if you recall, this function is actually differentiable at the point, complex differentiable at the origin. Except origin, it is nowhere differentiable. So even if it is differentiable at the point 0, but it is not differentiable any near about point, okay, around 0, so it is nowhere differentiable, so therefore my function is not analytic because it is differentiable only exactly at one point. So it is differentiable at the point 0 and it is not differentiable any point in C minus 0, so this function is also not analytic. Next I will talk about what is called analytic at a point. So first I have defined analyticity on an open set. What is the definition of analytic at a point? So if I have a functions from D subset of C to C, and suppose I am considering a point z naught in D, then I am saying that a functions f is said to be analytic at a point z naught. So well, I need to just catch the above one. What is that? So to talk about the analyticity at a point, if there exists an open neighborhood in z naught which is contained in G such that f is analytic on that open set in z naught. So that means such that f is differentiable at each point of in z naught. So that means if I have a functions from D subset of C to C and take a point z naught in D, if I say that my function f is analytic at a point z naught, that means there exists a neighborhood around the point z naught which is sitting inside D, and my function is analytic on that neighborhood. That means my function is differentiable at each point on that neighborhood. Further, f is said to be analytic in D. So this is analytic at a point. Now analytic in D means my function should be analytic at each point. Okay, so analytic in each point. This is one note. So that terminology is analytic, holomorphic and regular. So different book has different kind of notions, like notations. Some book it says that it's analytic function, some book holomorphic, some book regular. I think if you go through Conway book, so they are having that holomorphic functions. Same definitions, okay, do not worry. In some books they are saying that it is analytic, some book they are holomorphic, some book is regular. Now there is a small kind of questions I am asking. Suppose f is analytic at each point or suppose AP is analytic at a point Z0. Now the question is, does it imply AP is analytic in an open set containing Z0? That is one. So at a point Z0, AP is analytic I have just given. Now will it imply that AP is analytic in an open set containing Z0? Now that questions I think maybe next class next lecture I'll talk about that yes, it is the case actually, but you should think. Because you see, if the way I have given the definitions is that F is analytic. First I started with the definitions, analytic on an open set. And then I am giving a definition analytic at a point, though I am saying it is analytic at a point, but I am keeping the definitions in a neighborhood, that means in an open set. So from the definitions it is clear, or maybe later on I will talk about that the analyticity, it's actually a set property. That means I can talk about analyticity on an open set, on a set. Okay, even if I am saying that it is a like analytic at a point, but I am talking about analyticity on an open neighborhood containing that point. So later on you will see analyticity is a kind of set property, whereas differentiability is a point property. That means I can talk about my function is differentiable at a point. However, whenever I can say that my function is analytic at a point Z0, that means I am talking about analyticity in an open set. That is why this question is there. Does it imply analytic in an open set? Answer is yes. So therefore, because if I take a small neighborhood, you see that's one small thing, Z0 is there. So if I take so analytic at a point Z0, that means what? There exists a neighborhood where at each point my function is differentiable. Now if I have a in Z0 neighborhood at the point Z0, now nearby Z0 there is another point. So this is also a neighborhood of that point also now. If I take a small neighborhood, there each function is differentiable. So therefore analyticity at a point Z0 implies that analyticity at neighborhood, very nearby point of Z0. So therefore analyticity here also it will imply analyticity at nearby point of that one. So therefore though I am talking about the analyticity at a point, but actually I am talking about analyticity on an open set. So therefore analyticity is a set property, whereas differentiability is a point property. So I can talk about differentiable at a point. So therefore you will have the examples where my function is differentiable exactly at one point, like f of z is equal to mod z square. However, you cannot have the example that your function f is analytic exactly at one point. No, you cannot have it. You have the examples of analyticity on an open set. So that is why this problem you should think. Even if my function is analytic at a point, it is implying that f is analytic in an open set. You can guess it here. So because if I have a neighborhood of in Z0, you take the nearby point and do the things, and then you can have the like argument like arbitrary union of open set is open. So therefore actually I am talking about analyticity on an open set. So therefore analyticity is a set property, whereas differentiability is a point property. In fact more I will talk about that. So because this is the kind of, so that means analytic definitions, it's a very strong definitions compared to the differentiability. Because differentiability I have a point where I can talk about the differentiability, but analytic means what? I need the differentiability at each point on that open set. So this is very strong compared to the differentiability. Analyticity is a very rigid property compared to the differentiability. It is a very strong property, and since it is strong and since it is rigid, you will see very nice theorem will come out in complex analysis. Because if I assume analyticity, very nice kind of behavior, very nice properties, very nice theorems will come out, because analyticity is very rigid. Because I'm demanding the differentiability of my functions at each point in a neighborhood of that point or in an open set. So that is why I should expect something extra if I just assume the differentiability at a point. Okay, so if I have a function which is just complex differentiable at a point, the kind of conclusions you will have it, the conclusions of the conclusions of these functions or some theorems, you will get it. It is not that like good. However, if I assume the analyticity, because analyticity, as I said, it is very rigid, I should have expect something nice conclusion, and answer is yes. Many nice conclusions, nice theorem will come, and more I will talk about in my next lecture. I think that's all for this lecture. Thank you.